Okay, let's get started with day 3 of our Isabelle lecture, lecture 3. Title a new section for day 3 lecture. And the focus of today's lecture will be on induction. We saw a little bit of very basic list induction before, but I really want to focus on more complicated, more complex induction proofs today. So let's look at, let's define a new function. Let's call a function, define a function called add_all. Pretty straightforward. That takes a list of integers and returns just an integer. And we're going to want to try to define that as the sum of every single element in the list. So we're going to define this recursively, which is why I wrote a function. Where add_all of the empty list should just simply be 0, or add_all of some non-empty list with the first element h and the second element t is going to be h plus the result of add_all on the remainder of the list. Right? If you can think it through, you'll see that this, you'll see why we define the empty list to add up to 0. Right? So just as an example, right, add_all of the list 1, 2, 3, 4, 5 is just 15. Right? 1 plus 2 plus 3 plus 5. That gives 15. Okay, sounds good. All right, we're going to define something relatively simple about this function. We're going to prove something relatively simple about this function. We're going to say, so we're going to prove a lemma that says what happens when we call add_all on a non-negative list. So we're going to assume that for all, I'm typing this for all symbol with backslash for all, and then you can press tab to select this. For all indices I less than the length of L, we have that the element at I, the ith element, is greater than or equal to 0, right? That every single element in this list is non-negative. And we're going to show that if we call add_all on L, it's also non-negative, right? That's as strong of a statement as we can write. If everything is non-negative, then, if at worst case everything is 0, so it's, the sum is worst case 0 as well. Okay, fantastic. So what we're going to do here is, of course, this add_all is defined inductively, so we should expect to do an inductive proof, right? So we'll start off with our usual induction. Gives us this thing right here, right? And then let's look at the base case. Okay, base case here looks pretty simple. That add_all of the empty list is greater than or equal to 0. Well, we know that add_all of the empty list is defined as 0. So if we simply do unfolding add_all.simps, right, we'll get 0 is greater than or equal to 0. That's trivial, proves by simp. Good. Now let's look at the next case, right, the inductive case. So the inductive case, it's asking us to prove that if we assume that add_all of L of the tail of the list is greater than or equal to 0, then when it has one extra element a, that this whole thing is greater than or equal to 0, right? And by the way, you don't have to, if you wanted to, you could rename the parameters of the way that this inductive of the way that this was set up, right? Like if we wanted this to be h and t instead, right? The goal would you can reflect variables. You can rename variables in this way. Okay, so we're going to try to prove this, right? But then very quickly, if I just do unfolding add_all.simps, we see that, well, this add_all of t, this term right here is non-negative, but then what about h, right? Like we are missing in some sense that this assumption about how every single element of the list is non-negative. We want an assumption that's saying that h is non-negative, right? Okay, and this is because we never actually used this assumption in our inductive hypothesis. I'm going to label this assumption as non-neg, and I need to use this non-neg assumption. And we do this by typing using non-neg before the induction setup, right? This using must come before the inductive proof, or else you're not going to get this, right? So for instance in here, right, yes, now we get this fact about, it looks a little bit complicated, so we'll break it down a little bit further, but at the very, there's some statement about things being non-negative, right? Okay, good. One thing I want to showcase is that before here, when we're using non-neg, this non-neg is referring to L, to this blue L that we originally defined. When we got down here, the inductive case renamed it into the variables into H and T, and so the assumption was turned into the variables in the assumption are also orange, right? If I typed using non-neg here, this is technically the assumption, but it has nothing to do with the inductive case that we're proving. This is a statement about the blue L. The case is only about the orange H and T's, right? So just be careful. When you're trying to use the assumptions in inductive hypothesis, it goes before the using, and be very careful about the color of variables to make sure that you're referencing the same thing, right? If I hadn't changed it from H to T, right, now this would be if I had this as A and L, right, now this would be quite confusing, right? This orange L and this blue L are not the same. They are different L's because they're different colors, right? So this is A, so I'll do this for H and T. This is easier to see, right? Okay, so now let's break down what actually happened when we added this new assumption into our induction. So first of all, you can see this has some semblance of the inductive hypothesis. The inductive hypothesis we had before is that add all of T is non-negative. However, when you add an assumption into an inductive statement, the inductive hypothesis gets an extra assumption that you must prove. You must prove that if this T is all non-negative, the inductive hypothesis now that if T is all elements of T is non-negative, then T is the add all of T is non-negative, right? And this second one is the original assumption, right? It's this add all of L applied to the entirety of the list, right? That the entirety of cons of HT, that H appended to T, is non-negative, right? Is what that reads. So I'm going to split this out. So first of all, I'm going to try to recover this line, right? This is the induct, so I'm going to try to prove, so we know that if every single element of H appended to T is non-negative, then of course every single element of T is non-negative, right? Because T is a sublist of, right, this list. So I'm going to try to prove this statement. This is the inductive hypothesis, and we're going to prove it by using cons, right? Cons of 1 is the inductive hypothesis. But in order to use this inductive hypothesis, we must satisfy the original constraint. So what we're going to do is just prove the original constraint, right? I can just copy paste this whole thing and try to prove it, right? I'll say this is the IH cond, the inductive hypothesis condition that will allow us to use the inductive hypothesis, right? So this can be proven using cons of 2, right? Like we mentioned, cons of 2 says that all elements of the whole list is non-negative. So of course, if just T is non-negative, right? We can see if, okay, and try 0 actually auto just proves this, right? A relatively simple statement for Isabelle. Automation to prove. Okay, now that we have IH cond, right, I can say using IH cond, right? And this does in fact match this, right? This statements read that if the condition is satisfied, then we can assume the inductive hypothesis. We've proved the condition, so we should be able to prove this, right? So if you do this, yeah, this will prove automatically. But I want to show something else, right? I want to highlight that what this double arrow does. Inside of Isabelle, this double arrow is what we call a meta-level implication. It's basically saying that you can, and the way that you can use these meta-level implications is that if you prove something, right, prove one of the conditions, you can discharge it. So what I mean by discharge is, I'll have that here for now, right? You can in a similar way, how you instantiated things in definitions and in definitions, you can instantiate conditions using a capital of. So if I type capital of ihcond, you can see, right, before, actually I want to show the before and the after. Right, before is right, we had this, right, this thing implies that, but then when we instantiate when we explicitly instantiate this condition, we're saying, okay, we've satisfied this, you can get rid of this, and that's what this line does, right? It takes an already proven fact and you can chop off the first condition in the inductive hypothesis. Okay, good. All right, and now this exactly matches what we wanted. So this will also prove simply by blast. All right, so now that you have the inductive hypothesis, let's see what else we have to show, right? So, okay, so now we have that t is indeed non-negative, so add all of t is non-negative. This is what we had before, add all of t is non-negative, right? We've gotten back to our original starting point, except we still have this assumption about everything being non-negative, right? We've originally used the assumption here to prove that the latter tail of the list is non-negative, but we can use cons 2 again to try to prove that h is non-negative, and that's exactly what we're going to do, right? So we're going to have, let's call this h non-negative, which just, h is greater than or equal to 0, using cons of 2, right? The second cons fact, right, for all I in the length, well, if I is 0, that's just the first, right, the first element of this list is h, tells you that that's greater than or equal to 0, so we can prove, right? Isabelle automation is good enough to just prove that, right? Okay, so now when we're showing this case, we can use the inductive hypothesis and h non-neg, right? That these two summons are both non-negative, therefore the whole thing is non-negative, right? That proves quite simply. Okay, sounds good. Bit of a more involved example, right? But this is a good example of how proofs can typically evolve in Isabelle, right? You start proving something, you're like, oh crap, I'm missing something, right? Let's go back and strengthen the induction, right? You strengthen the inductive hypothesis, you get an extra assumption, but you also get an extra proof obligation to use in order to use the inductive hypothesis, right? So there's sort of a trade-off there. Right? When you're trying to prove something, if you want to, in inductive proof, you can assume more, but also means you have to prove more to use that hypothesis. Okay, sounds good. Let's look at a different example, but similar. Right? So let's say what happens when we have when we run this add-all function on a strictly positive list, right? So first of all, we're going to assume that, so we're going to assume that for all I is less than the length of L at I is not only non-negative, it's actually strictly positive. And we're going to try to show that add all of L is greater than 0. Some of you might immediately be complaining and being like, wait, what if L is empty, right? Auto quick check got there first. If L is empty, this whole thing is just 0. So this doesn't hold. So I'm going to go ahead and add an extra assumption, right, for this lemma to actually be true, which is that L should not be empty, right? Now that L is not empty, if we just hold it here, we could also, so using the assumptions, we can run nitpick and quick check, right? This was the counterexample search tool, and both of them should not find any counterexample because, well, this is in fact a true lemma, right? Okay, so I'm going to go ahead and delete those. All right, so we know we have to be using the assumptions when we set up our induction. So proof induct on L. We're going to go ahead and click into that. Okay, good. All right, now let's examine what cases we have, right? Case 1, well, the base case is already starting to not really make sense, because we're starting with this empty list is not equal to empty list, right? Because the base case is actually when L is empty, but we're assuming L is not empty. So our base case isn't really the empty. We don't really want it to be the empty list. We want it to be when the list is of length 1, right? So the way that we do that is rather than inducting on the list L, we can induct on the quantity length of L minus 1. Induction always starts at either 0 or for natural numbers, or nil for lists, right? And what this does is going to give us a new inductive setup. I'm going to go ahead and delete this part. It's going to give us a new inductive setup where now our base case is with the length of L minus 1 being equal to 0, which makes the length of L equal to 1. So that makes us gives us that base case, right? Okay, and that's why we induct on the length of L minus 1, right? If we had inducted on the length of L, base case is length of L equals 0, L is empty. Well, we assume L is not empty, right? Run the same issue. That's why we have this minus 1. So you can induct on arbitrary quantities, right? Okay, good. And it won't always make sense, right? So make sure you're inducting on something that makes sense. Cool. So let's continue. We've shown here that the length of L is equal to 1. I'm going to go ahead and just rewrite that. Just have a lane L, that the length of L is equal to 1, right? Using the name of the case is 0. So when I type using 0, it has all the facts that are available to us in this case, right? So 0 of 1, it's a little bit of a strange syntax, but gives us just that first one. And this should, really? Oh, sorry. Okay, so this is a fun little case where a lot of first-time Isabelle users will run into, where, okay, seemingly, right, this equation looks like the length of L minus 1 is equal to 0, so of course length of L should be equal to 1. You can move the 1 over, right? But actually try 0 isn't able to prove it. This seemingly very obvious fact, because length of L, length, is defined as something that returns a natural number, and if the length is 0, then we are going to get an expression of 0 minus 1. So I'm going to go ahead and show that in the value command, but when you do 0 minus 1, when both are natural numbers, it's actually defined, right? The output is actually just 0. Because if you're in the type of natural numbers, well, how else do you define 0 minus 1, right? There's nothing it could possibly be. So it's this like ill-defined, you don't really want to ever be hitting this case ever, right? It's not, you don't want to be hitting that case. And so what so the other fact that we need is also this second fact about L being non-empty, right? We want to know that the length of L is not in fact equal to 0. Is not in fact equal to 0, right? So we'll say using the first bullet and the second bullet. And now let's see if this will prove. Oh man, maybe this may be a sledgehammer proof. When you run into these sort of corner cases of natural arithmetic, automation gets a little bit strange. So, okay. Sledgehammer was able to pull together a lot more of these lemmas. Okay, good. We have now proven that in the base case, the length of the list is 1. So now you want to say something along the lines about, L being greater than 0, right? Right, because, if you say you're using 0, right, the third bullet of this case is that every element of L is greater than 0. But we know that L just has exactly one element, right? And so, we want to say that L is it's equal to something, right? It's equal to some singleton list. The way we're going to do that is by using the obtains keyword. We're going to say we know exactly that L has exactly one element. We're going to obtain this element. We can name this element arbitrarily. Let's call it X, right? X is of type int, where L is, in fact, just the singleton list containing X, right? And the way that we're going to prove this is by using len L, right? We need to know that the length of L is equal to 1. Don't mind this. Sledgehammer will usually prove these sort of statements, right? If you just want to pull something out of thin air, right? Obtains is the keyword for you to be able to do that. Okay, and once you're able to obtain this X, well, right, we want to be able to, say that have that X is greater than 0. This is true because of 0 of 3, right? It says that every element of L is greater than 0. X is the only element of L, so X is therefore greater than 0, right? But we need a connection between L and X, and that's what this L is fact is, right? I named this fact. The name of this is L is. So I will go ahead and do unfolding L is to inline replace L with X. And let's see, will this prove? Yep, simple automatically prove this, right? So let's call this XPOS, right? So now when we're trying to show the case, right, this L, well, unfolding L is turns into just X, right? And then we can also unfold the definition of add all simps, and actually it will tell us that it's just X plus 0. And then if we use this XPOS fact that we just proved, right, that's trivially true. Okay, all right. Cool, we proved the base case. Now we have the inductive case, right? So let's tackle that. So let's take a look here. The inductive case looks a little bit more complicated. As we expect, in order to use the inductive hypothesis, which is this first bullet right here, right? This inductive hypothesis is something about, something smaller and so on and so forth, right? This L is, something like that, right? Now L is suck X plus 1, so L is going to be suck X is 1 plus X is the successor of X. So L is going to be at least 2, right? It's going to be 2 plus some number X, right? So okay, let's maybe try to prove a fact like that first. So that the length of L is at least greater than let's say greater than or equal to 2, using the name of this case is suck of, so we'll count suck of 2 gives us something about the length of L. We don't want to be doing arithmetic when with natural numbers when it's 0 minus something. So we need this L as non-empty fact as well. So that's bullet 2 and bullet 3. So we'll use suck of 2 comma 3 to try to prove that the length of L is at least 2. Right? This one, I imagine, the last one was a sledgehammer proof. This one will probably be a sledgehammer proof as well. Actually, I was very wrong. Lin arith should just solve it. So try 0 here would have found all of these proofs too. But anyways, okay, good. right? And then we can try to keep going, right? So so I'm going to say, okay, let's look at using suck again, right? Suck has every single fact available to us in this case. Let's try to look at the inductive hypothesis, right? The inductive hypothesis says that if you have, some length L, if you have some list that's the length minus 1 is the length of this list is at least 1, right? Is what this reads. X is any arbitrary natural number, so this reads that the length of L is at least 1, and L is non-empty, and all the elements are positive. Then add all of L is greater than 0, right? But this is kind of exactly what we wanted to prove already, right? Like it's something feels a little bit fishy here, right? The goal is this, but that's the inductive hypothesis. And if you look at it a little bit more closely, this condition on L contradicts the actual length of L, right? The actual length of L is x plus 1 is x plus 2. This one is sort of saying that you can only use an inductive hypothesis if the length of L is x plus 1. So we'll never be able to use this inductive hypothesis because we don't want to apply the inductive hypothesis to the full length L. We want to apply the inductive hypothesis to like the tail of L, right? Like L, we want to say that, okay, if the length of L is at least 2, then L is equal to something along the lines of h appended to t, and length of t is at least 1, right? That's really what we want to do. And length of t would satisfy this assumption about it's it's not empty, right? Okay. So something about this inductive setup is not working. And the way to fix this is we want to generalize the inductive hypothesis. I don't want the inductive hypothesis to just apply to L. I want it to apply to to any list, right? Any list that satisfies these conditions should be able to, any list that's smaller than L, right? It should be able to have this inductive hypothesis. The way we do that is with the arbitrary keyword. So when I write arbitrary L, you can immediately see, oh man, well this list broke. This proof broke. I'm going to go ahead and fix this proof and be right back. Okay, so here we go. We have a new suggested proof by Sledgehammer. And this happens every now and then, right? When you change the proof setup, previous step, may break in minor or major ways, and you will have to go back to fix them, right? In this case, Sledgehammer was just able to find an alternate proof to make this line go through. But more importantly, I care about what happened to the inductive hypothesis, right? And you see here that, this is super interesting, that if you can prove for any arbitrary list L, right, this is now a question mark L, is different from this orange L, is not the L that we're working with, then you can assume that the add all of that smaller list is greater than 0, right? And now the question is, well, what should we instantiate this L with? Well, we already said, right, that it should be the tail of the list, right? It should be the latter part of the list. Because when we're usually inducting on a list, right, when we define add all, that's how we defined the recursion. So I want to write this, right? I want to rewrite L as some list, as some element h appended to some list, some tail t, and the length of that tail is at least 1. And we are going to, again, use the obtain keyword, right? Now we're going to obtain two things, the head and the tail, where, first of all, L is equal to h appended to t. And furthermore, and is again a keyword, the length of t is greater than or equal to 1. Notice that if I don't write this second part, I'm losing information. We know the length of L is at least 2, right? It has at least 2 elements. There's one of its elements. Well, T has another one of its elements. So if I don't write this line, I won't have access to the fact that this T should be having another element, right? So I'm going to use, I'm going to call this fact len L again. So using len L, right? Usually when you're trying to obtain something, you do it via sledgehammer. We will see cases in the next lecture where that's not the case. But okay, so sledgehammer is able to easily get that for us, right? I'm also going to label this L is and call this lang of T, so that I can reference this fact later on, right? So now when we're using sucked, well, we know that this L is going to be, we know that we want to instantiate this L with T. So I'm first going to say, okay, so this suck has 4 bullet points. We're only interested in the first one. And then we're going to want to instantiate this L with T, right? Okay, cool. Now, we have a few things, right? First of all, we want to prove this fact about the exact length of T, and then we want to prove this fact about T being non-empty, and then we have to prove that every single element of T is positive before we can assume this, right? So these are 3 conditions we have to prove. We're just going to write those 3 out, right? So I'm going to go ahead and copy-paste this to be able to use for our inductive hypothesis. To be able to prove our inductive hypothesis, right? So the first condition is that this thing has to be an exact length. I'll just sorry it out for now. Con 2 is that T has to be non-empty. Sorry it out for now. Con 3 is that this all elements of T is non-negative. Sorry, is positive, sorry it out for now, and this should be able to give us the inductive hypothesis, which is that add all of T is strictly greater than 0, right? So now I'll say, actually using suck1 of T, right? This is where we were before. I was sort of using this space as a scratch pad to sort of play around with what things look like, right? Okay, and now, assuming that we can prove all 3 conditions, we can instantiate these conditions directly in because we have these double arrows, right? I think we saw a little bit of this last time, or maybe it was this lecture. But you can do that within the same block, within the same of block by just having a comma and then continuing with this capital F, right? So you can mix lowercase and capital F's, right? Like a nice little quality of life thing, right? Of con 1, that gets rid of the first condition, con 2 gets rid of the second condition, con 3 gets rid of the third condition. You end up with the exact IH that we want, right? This will prove by blast. Okay, so now we have to go back and actually prove conditions 1, 2, and 3, right? But this is relatively simple. Using suck has everything we need, right? Suck has this second fact about the exact length, and then we also want to be unfolding L is, so that we know the relationship between L and X and T, right? This will probably just prove. Very good. Right, second condition, again, we're going to be using suck of, well, this one we don't even need it. We just need length of T, right? That if the length of T is at least 1, then of course T is non-negative. By auto, this proves. Very good. And then condition 3, now we're going to be using suck again. Suck of 4 is the one that guaranteed all elements of L are positive. So I'll go ahead and type suck of 4. I want the connection between L and T, so I'll unfold L is, like that. Right, now okay, now everything's in terms of T. See if that proves. Good. Auto is automatically able to prove that. Right. Auto has gotten better over the years. I do remember 1 or 2 years ago that Auto was not able to automatically prove this statement, and you have to do a little bit more with Sledgehammer. But the Isabelle developers are some of the most amazing people I've met, most smartest and some of the most intelligent people I've met. Okay, good. So now we have this add all of t is greater than 0, right? So, okay, well, we know something about t being positive. So now if we use, if we unfold L is, right, t, what is it? No, L turns into h appended to t, right? And then we can unfold add all dot simps. It will do h plus add all of t. We've just proved via the inductive hypothesis that this is positive. We next have to prove that h is positive. So have h is positive, greater than 0, probably using suc4 again. This was the thing about everything being positive, right? Unfolding L is, let's see if that proves. Good. Very nice, right? And then so then if we say using the inductive hypothesis and h pos, all the sum ends are positive, so of course the sum is positive, right? Okay, very good. And so that sort of shows a nice example of how, you're going all in a proof, right? You're like, oh crap, the inductive hypothesis isn't quite what I expected it to be, right? Arbitrary is a really useful technique to set up the proof so that your inductive hypothesis is more arbitrary. You can use it for arbitrary things that are a smaller measure than whatever you're inducting on, right? Okay, sounds good. We're going to look at one more example before the end of this lecture. And so I'll set that up and be back. Okay, so here we have a inequality about natural numbers, in particular about the fact that for n large enough, in this case 3, that an exponential function is going to be larger than or equal to this linear function, right? Okay, sounds good. So we're going to try to prove this. This is actually a very textbook style. This is actually a very classical induction proof on n. Right, and I'm going to try to showcase what this might look like. So we're going to start doing induction, right? We know we want to induct on n. The base case is n equals 3, right? We're going to try to show that if n is equal to 3, that this holds trivially, 8 is greater than or equal to 8, and then every here on after, we assume the inductive hypothesis, try to show that this inequality works. All right. So we're going to be inducting on n. But if we induct on n, it makes n start at 0. We want it to start at 3. So, okay, one way to do that is we can just induct on n minus 3. To my knowledge, there is a much more elegant way to do this. There is like a induction rule that lets you make a quantity start at the place you want it to be, as long as it's bounded from below. Maybe I'll put that in the notes if I find it again. But anyways, so this is the inductive setup. All right, and here this is the goal. We're saying, okay, n minus 3 is equal to 0. Oh, we need to assume this fact that n is at least 3. I should say using the assumptions. All right, so then n is greater than or equal to 3, so therefore n is equal to 3. Maybe I'll just say have that n is equal to 3 using 0 by auto. All right, I'm going to call this n3, n is equal to 3. Right, then if I say unfolding n3, 3 plus 5 is less than or equal to 2 to the 8th. This will probably just prove. Good. All right. Next, we get to this to the successive case, right? The successive case is saying that, okay, if right, so in this successive case, it's saying that n minus 3 is 1 plus something, right? That is, it's not equal to 0, it's at least 1. 1 plus something, right? So n is equal to x plus 4, right? That's what this reads, n equals to x plus 4. But then the inductive hypothesis, we're running into the same issue as before, right? In order to use the inductive hypothesis, we have to know that n is equal to x plus 3, but n is equal to x plus 4. So let's make n arbitrary, right? Let's adjust the inductive setup, arbitrary n. The earlier part of the proof didn't break. This is good. And now we can instantiate this n, right? Okay. Sounds good. So this part right here, first of all, gives us that n is equal to x plus 4. I'm going to go ahead and just write that down. Have n is equal to x plus 4, just for our sake, right? I'm going to label this as n is, because it says what n is equal to. Using suck of 2 and 3, try 0 will prove it automatically, right? Okay, sounds good. Now we want to use suck of 1, and we're wondering what to instantiate this n with, right? Well, this actually gives you a very strong hint for what to instantiate n with, right? Well, this one says n is equal to x plus 4. So now this is asking x is equal to what minus 3? Well, then x is just equal to n minus 1 minus 3, right? X is equal to n minus 4, so we want to pattern match this with the minus 3, so we actually want to instantiate this with n minus 1. Right, okay. And then it will, we have to satisfy these two conditions to use the inductive hypothesis. So I'll go ahead and call this con 1 is this one, right? I'm copy pasting directly so that I can pattern match it later with the big of instantiation. Using n is will probably do the job by auto. And then the second thing we have to prove that is that n minus 1 is at least 3. Have con 2. And is will probably also, again, do the job. Very good. All right, so now this whole thing turns into of con 1, con 2. Oh, sorry. Comma. Of con 1, con 2 to tell us that n minus 1 plus 5, that for the particular instantiation of n plus of n minus 1, that this statement holds, right? That when you plug this n with n minus 1, right, it's the inequality holds, and we want to prove it for what happens when it's n, right? Okay. So let's try to prove that. We know that 2 to the power of n is twice of that, right? So I'm going to go ahead and rewrite this one. Have 2 times 2 to the power of n minus 1 using n is. Really? Oh, well, I need something about the fact that n is at least 1. So a sledgehammer will probably do it here for us. Yeah, okay. Good. And then I'll say this is, so which side was that? That was the right-hand side. I'll label this as RHS. So then here, if I do unfolding RHS, it's now able to give that, right? But then, well, this is strictly greater than n plus 4, and then 2 times n plus 4 is going to be 2n plus 8, which is strictly greater than that, right? So let's spell it out. We're going to prove that this thing right here, right, have that this is greater than or equal to 2 times, where's the inductive hypothesis? This quantity right here, which is n plus 4. And I should, I'm realizing now that I should really just have this. I really should have just split this out as the inductive hypothesis. That's my bad. So I'll explicitly label a fact as the inductive hypothesis, right? That 2 to the n minus 1 is greater than or equal to n plus 4. Using exactly this. This will prove. Now this fact will prove using the inductive hypothesis. Good. Right? and then we're going to want to, I'll just say then show. I don't feel like labeling it, so I just want to pull this directly into this proof case, right? That if you know that this quantity is greater than or equal to this quantity, hopefully Isabelle will be able to see that this quantity is greater than or equal to this quantity. And indeed it is able to. Okay. The automation could have done more heavy lifting. I wanted to be a little bit more clear with how exactly that proof is going. All right. Okay, sounds good. So those are some more interesting inductive examples of when you might need to strengthen an induction, right? Don't forget to use your assumptions in an induction, but be careful about adding assumptions in an inductive proof because you incur extra goals. Right? Okay, this is a good place to leave off.